Application: Theoretical Approach to Probability. In this module, you will learn to solve the applications of the theoretical approach to probability. Suppose you are in a game show. The game show has a host named Dave who shows 3 boxes to you. Now, he shows you the prizes inside the boxes. Inside one of the boxes, there's a star prize of a cycle, whereas the other 2 boxes contain a toy car. On changing the place of the boxes, he asks you to select any one box from the given 3 boxes. You have no way of knowing which box conceals which item, and on picking which box, you will receive the star prize. Now, can you answer what will be the probability of winning a cycle? Yes, the probability of winning a cycle is 1 upon 3, as there are total 3 choices, out of which only 1 box is containing the star prize. How many possible outcomes are there by throwing a dice? As we know, the total possible outcomes are 1, 2, 3, 4, 5, and 6. Can you find the probability of getting 1, 2, 3, 4, 5, and 6? Yes. As we know, the number of possible outcomes is equal to 6. Let us say that A be the event of the dice showing up to 1. Let B be the event of the dice showing 2. Similarly, let C, D, E, and F be the events of getting the numbers 3, 4, 5, and 6 respectively. The number of outcomes favorable to A is 1. Therefore, the required probability of getting an event A is 1 upon 6. Similarly, as the number of outcomes favorable to B, C, D, E, and F is 1, therefore, the required probability of all the given events is 1 upon 6 each. As we notice that all the events are having only one outcome, therefore the events are called elementary events. Also, if you observe, sum of the probability of all the elementary events of an experiment is 1, which is true in general also. If the dice is thrown twice, then what will be the number of possible outcomes? As we know, a single throw of a dice results in 6 outcomes. So, if our first outcome is 1, then on throwing the dice again, we have 6 options or outcomes: 1, 2, 3, 4, 5, and 6. And the same goes on if our second outcome is 2, then it also has 6 options or outcomes. Similarly, it goes the same for the other outcomes also. Thus, with the help of these, we can find the exact number of possible outcomes for this scenario. As 1 comes on the first throw of a dice, and then 1 on the second throw, another is 1 on the first throw and 2 on the second throw. You could also get 1 on the first throw and 3 on the second throw. Similarly, by doing the same, we get the following outcomes. And we have seen, we have 1, 2, 3, 4, total 36 outcomes. Now, can you calculate the probability that the sum of the 2 numbers appearing on the top of the dice is 6 if the 2 dice are thrown at the same time? As we have seen that on throwing 2 dice at the same time, the total outcomes are 36. Let E be the event of getting the sum of the 2 numbers appearing on top of the dice as 6. Now, let's note down the outcomes which satisfy the given condition. These are 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. So, here the favorable outcomes are 5. Thus, by using the theoretical approach of probability, the probability of E is equal to 5 upon 36. As it is already in the simplest form, it is the required probability. Have you seen the deck of playing cards? many cards does this deck contain? It contains a total of 52 cards. These cards are divided into 4 suits. These are clubs, spades, diamonds, and hearts. The suit of clubs contains 13 cards. Similarly, the suit of spades, diamonds, and hearts also contains 13 cards each. It shows that each suit has 13 cards. Now, look at the cards of each suit. It shows that the cards in each suit are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Also, if you notice, each card of the same suit depicts the same symbol. Here the cards, jacks, queens, and kings are called face cards. Similarly, on observing the other suits, we observe that the suit of the cards of spades also have the same cards like ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king, except the symbol. All the cards are having the same symbol of spades. Now, on observing the other 2 suits, we observe that both the suits are depicted with a symbol of its suit. One more thing if you notice here is that all the cards are having only 2 different colors. Can you tell me the colors the cards are having? These are black and red. Now, if I ask you to draw a card from a well-shuffled deck of 52 cards, then can you calculate the probability that the card will be a king? As we see that there are total 4 suits and each suit is having a single card of king, which shows that there are total 4 kings out of the total 52 cards. Thus, it shows that here the favorable outcomes are 4 and the total outcome is 52. Thus, the probability of getting a card of king will be 4 upon 52, that is 1 upon 13. What if I ask to calculate the probability that the card drawn is a red king? As we know that out of 4 kings, 2 cards are red and 2 are black. Thus, here the favorable events are 2, and on solving this fraction, we get 1 upon 26, which is the required probability. Next, what if I ask you to calculate the probability that the card should not be a king? Then what will you do? As we have seen that the total number of cards of kings is 4. Therefore, the non-king cards will be the difference of the total number of cards, and the cards of kings, that is 48. Here, the favorable outcomes are 48. Thus, the required probability of getting a non-king card is 48 upon 52. On simplifying, it gives a fraction of 12 upon 13, which is the required probability of getting a non-king card. There is one more way to calculate the probability of getting a non-king card. As both the events, say E, getting a card of king, and say F, not getting a card of king, are opposite to each other, so the probability of F is nothing but a complement of E. Thus, the probability of both the events will be complementary to each other. As we calculated, the probability of getting a card of king is 1 upon 13. Thus, the probability of getting a non-king card is 1 minus 1 upon 13. That is 12 upon 13. There are many more different examples. In a figure, point A, B, C, and D are the centers of 4 circles, each having a radius of 1 unit. If a point is chosen at random from the interior of square ABCD, can you find the required probability that the point will be chosen from the shaded region? Yes, here the favorable outcome is the shaded part of the figure, as we have to find the probability that the point will be chosen from the shaded region. The area of this shaded part is the difference of the area of a square and the area of 4 sectors, as at each corner point of a square, a sector is formed. Also, here the area of a square shows the total possible outcomes. So, the required probability will be the fraction of area of the shaded region upon the area of square ABCD. Now, our first target is to find the area of the four sectors first. As we know, the area of a sector is theta upon 360 multiplied by pi r square, and the measurement of each angle of a square is 90 degrees. Thus, the area of four sector of a square is 4 into 90 upon 360 multiply pi 1 square. The radius of a circle is 1 unit. Now, on solving it, we get the area of four sectors as pi square units. Next, our target is to find the area of a square. If you see here, these are the radii of these two circles, and we have given that the radius of a circle is 1 unit, so the radius of these two circles is 1 unit each. It shows the side of a square as 2 units. Also, as we know that the area of a square is side square, thus, the area of a square is 2 squares, which gives the area of a square as 4 square units. So, the area of the shaded region is 4 minus pi square units. Thus, the required probability is 4 minus pi upon 4. Let's recap. On throwing a dice twice, the total outcomes is 36. There are 52 cards in a deck of playing cards. The deck is divided into 4 suits of 13 cards each: spades, hearts, diamonds, and clubs. Clubs and spades are of black color, while hearts and diamonds are of red color. The cards in each suit are ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and 2. Kings, queens, and jacks are called face cards.